So hi everyone. In this video, we're going to start the unit about normal function field extensions, and I need some prerequisites about group actions. So if you know what a group action is, and what is the orbit stabilizer theorem, which is the most sophisticated machinery that we need for group actions, then you can easily skip this video. We're going to use standard notations, so no worries. And if you don't know that, then it's a good place, you should definitely see this video, but I also, again, would refer you to Richard Borchard's fantastic videos there about this topic. He has a course about group theory also, and there is a very nice example there as well. So anyhow, do watch this video if you don't know what a group action is. It's a very simple and basic notion, and otherwise feel free to skip it. Okay, so this is the unit. So in this unit, we are going to, again, talk about group actions. And then the next 3 points here, which I'm not going to do in this video, are just the basic of Galois theory. So there is a couple of lectures that I put on about Galois theory, which are much more extensive than those. These are just like a recap about the actual definitions without any explanation whatsoever, definitely no proofs. So I would ask you to make sure that you know everything here, and if not, you should go and see the previous videos. But generally, as a prerequisite to the course, you need to know Galois theory. We will do one thing which is non-trivial, and people usually don't do it in a Galois theory course in the next video, and then we're actually going to start. Okay, so 5 up to 9 are the items of this unit that talk about normal function field extensions. And if you remember, I told you that the ramification index and residual degree can be understood as a size of some groups, and these are called the composition group and inertia group. We will see. And so what will happen really is that you will have, just to have some context, you're going to have some prime divisor, maybe little p here, and there are going to be some prime divisors above it. And what will happen is that the automorphism group of f over e, kind of hiding L and K here, L will usually be K, it turns out that it acts on these prime divisors. Namely, if you apply an automorphism on the function field, it induces an automorphism that will send maybe this to that place and maybe some other place to itself, but never to a place that sits above another prime divisor. So there is a natural kind of group action that is induced by the group of the Galois group of f over e, if f over e is normal and separable and so forth. So because of that, I need you to know what a group action is. Okay. Anyhow, so let's just start. Again, this really has nothing to do with our course, but since I'm assuming that we are all computer scientists, we usually don't see that notion. Okay. So what is a group action? So let's say X is a set and G is a group. X would be any set, but G has to be a group. And throughout, I may forget to say it, but in some cases, I will need G to be finite, so not now, but at some point. A group action alpha of G on X is a function. Technically, it takes an element in G and an element in X. I say technically because in a second, we won't think of it like that. Anyhow, it takes an element in G and an element in X, and it produces an element in X. So, G comma X go to an element, and that element is usually denoted by Gx. So it's like G times X or G like applied to X, but you don't even put the parentheses. And note also that when you write it, you don't reference alpha whatsoever. So there could be like some two group actions, alpha and beta, and when you write it like that, you can differentiate between the two, but that won't be a problem. Usually you'll have only one group action. Okay, but anyhow, not any function from G times X to X is a group action. It has to kind of respect the group structure, which is the only structure that you have here. So first of all, you want that Ex is X for every X. Okay, so the identity acts kind of as the identity. And you want that if you apply the G element to the element from X you got by applying H to little x, it's the same as if you first compute within the group what is G times H, and then you apply that element to X. It's like associativity, but yeah. but not quite, because these are different types. Okay, and if you have that, then the group G is said to act on X according to alpha. You could have other rules of action, but other actions, but you said the G acts on X. Now, some basics. Know that the function obtained by fixing G and look at the function that sends X to X, let's call it phi sub G, which really maps X to G of X for the fixed G that you have. That's a bijection. Okay, so for every fixed G, phi sub G is a bijection. Like this phi sub G, which just multiplies by G, or it acts by G on X. So Y. So let's first say that it's 1-to-1. So if phi sub G of X is phi sub G of Y, it really just means that G of X equals G of Y by definition. And now G is a group, so you can apply G inverse to both of these elements from X. So you'll get that G inverse Gx is G inverse Gy. And now, according to the first rule that we had here, or second rule actually, you can first compute this element, which G minus 1G, which is in the group, and then apply it to X and to Y. We get the same thing. I mean, this equals to this and this equals to that. And since this is E and also this is E, we get that EX equals EY. But then by the first item, we know that E is the identity, which means that X, I mean, this is X and this is Y. So it means that X equals Y. And so all in all, we got that phi sub G is injective, 1-to-1. It's also onto, because if you give me an X and you ask who's the preimage of X according to phi sub G, then it's just G inverse of X, right? Because phi sub G of G inverse X is, well, by definition, G times applied to acts on G inverse X. And then you can, by the associativity, do the calculation in the group. So G inverse X, which is EX, which is X. So we all know that group theory is about symmetries, and in what sense? So take, for example, a setting in which you have a triangle sitting in some, I'll do my best here, like that. They should be like 60 degrees each. Same sizes, of course. So if you take this triangle, which its middle should be in the middle of the axis, but I didn't manage to do it, and you rotate it, then if you do it in 60 degrees, no, 120 degrees, the triangle will look as if you didn't move it, right? So there's this action on the entire plane, which will get the triangle back to its original position, because you don't distinguish these vertices or edges. So really, if you think about it, in a sense, symmetry is a bijection. Okay, so formally, a symmetry of a set X is just a bijection from X to X. So in this case, rotation by 120 degrees. But you can also have a reflection around this axis, for example, or this axis, or rotation in the other direction, and so forth. And if you can think of the set of all symmetries, namely all bijections from X to X, this is not just a set, it's actually a group, because if you compose bijections, you get a bijection, and you have the identity like do nothing bijection, and you can invert a bijection. So it's a group, and that group is denoted sim of X, like the symmetry group of X. Now, how does this relate to what we did? So by the previous observation, we know that if G acts on X, according to some alpha, which we kind of omit in our notation and discussion, then every little g, every element in the group gives rise to an element phi sub G in the symmetry group, right? Because we just said that once you fix little g in G and you act according to this little g only on X, you get a bijection. So what I'm saying here is that every little g in G, once you set an action of G on X, it gives you a symmetry. It gives you an element, a bijection in a symmetry of X. And not only that, the mapping that takes an element from the group to this group, I mean, these are two groups, it's a group homomorphism. Namely, if you map G to phi of G, and then you take another H, then and maps and apply that, then you get what I'm trying to say is you get this. So phi of GH is the same thing as composing phi G on phi H. So a composition of the corresponding symmetries, you can do it by just consider the symmetry of the product within the group of GH. And also E goes to the identity on X, right? Because phi of E is the identity, which is the identity in the symmetry group. And so how do you see this? And just, it's really part of it's kind of obvious. The one thing that's not obvious is to figure out what's going on here, but verifying this is obvious because phi sub GH of X by definition is GH applied to X, which then by the rules of group action is G applied to HX, but HX is phi sub H of X. So you have this G applied to phi sub H of X, but G applied to anything is phi G of that thing, and then that is just a composition, right? And you usually don't denote phi G by phi G, you just denote it by G. So G goes to G in this sense. But the element G as a bijection, you think of it as multiplying or acting from the left by G. Okay. So we need a couple of definitions about group actions. So first of all, an action of G on a non-empty set is called transitive if you can reach from every element to every other element using some element in G. Namely, for every X and Y in your set, there is a group element that when it acted on X will give you Y. Okay, and there is a nice graph that you can have in mind while talking about this. So the vertices of the graph are the elements of X, and you have the edges. So an edge from X to Y labeled by G means that Y is G applied to X. Okay. So when I say that a group action is transitive, I mean that this graph is transitive in this sense. Like you can get from anywhere to anywhere. By the way, if you have X, G, Y, then you have Y, G inverse X, right? Because if G applied to X give you Y, then G inverse applied to Y give you X. You can see that because if this is true, then you can apply G inverse to both sides. And then this is, G inverse G X, which is just EX, which is just X. Okay? So in a sense, you don't even, maybe you sometimes don't even want to write the arrow if you don't care about whether you apply G or G inverse, but never mind. So transitive means that, between every two vertices here, you have an edge either in this or in that direction. And the orbit of an element X, under again the fixed action, is all the vertices that you can reach from X using G. So it's really, you go over all possible geox for every G and G, which in the graph presentation, this is, you iterate over all possible G's, and you ask where are you getting to. Okay. I mean, of course, it could be the case that you have several, so maybe GX and HX are the same, right? So it could be the case that both, G applied to X and H applied to X can give you the same thing. We just say that applying G is bijective, but we didn't say that you don't have collisions in between these bijective maps. So applying G to X and H to X might give you the same thing. Okay, so anyhow, the orbit is, where can you reach from X using the group? And if you think about it for a second, then the orbit form a partition of X. So this gives you an equivalence relation, right? So you will say that X and Y are equivalent if their orbit is the same. And it's an equivalence relation between, it's an equivalence relation because you always have the identity element that will map to yourself. So that's the reflexive property. And there is symmetry because that's what we wrote about the G inverse here. If you can reach from X to Y, you can reach from Y to X using G inverse. And there is transitivity. If you reach from X to Y and from Y to Z, maybe using G and H, then you can use GH to reach from X to Z. It's an equivalence relation. For example, saying that the group action is transitive says that you have a single orbit. There is one class. You can reach from anyone to anyone. Now, the set of all orbits of X we won't need that, but I just said it once. So the set of all orbits of X under the action of G is sometimes denoted like that. So you kind of you mode out by the group action, and that gives you what's called quotient of the action. But it's kind of important enough to say, but I don't really need it in our course. So the other important definition is the following. So when Gx equals X, we say that, well, G fixes X, but we also say that X is a fixed point of G, right? Depending on your perspective about if you think of X or G. And it's the same thing. But for X in X, the stabilizer subgroup of G with respect to X is given by this thing. So the stabilizer subgroup of X in G is this G sub X, which is just all elements in the group that maintain whose X is their fixed point. So in terms of the graph, these are the self loops. So if you have X, so every element G that satisfies that is in G of X. It's called the stabilizer because it keeps X in place. And for example, observe that if you take two elements in your set, X and Y, such that Y is Gx, then the two stabilizers satisfies this relation. Right? They are conjugate of one another. Well, I should have said this is indeed a subgroup, right? Because if G fixes X and H fixes S, then G after H fixes X. And if G fixes X, so its inverse fixes X and the identity fixes X. So this is a subgroup, and this is these two subgroups are conjugate if you can reach, according to G, if you get Y by applying G to X, Gx. So in terms of graphs, this little claim tells you that this equality tells you that if you have X and Y, and Y is obtained by applying G to X, then on the right-hand side, so on the left-hand side, you have self-loops of Y, and they are obtained, as it says like here, all of them are obtained by doing the following. So first of all, going back, so doing G inverse, then take a self-loop that's an element in G of X, and then going back to to Y using G. So the self-loops, right, if you can reach from X to Y using G, you can relate the self-loops of X and of Y, which in this language, these are the relation between the stabilizer subgroups. So the stabilizer of G of Y and G of X are conjugate with the corresponding G. Okay. So now this is the last thing I have to say about group actions. So let's say fix some X, and let's say that you have a collision between G of X and H of X. Okay, so let's say the G of X and H of X are the same, meaning H inverse G of X is X. You see, I don't even use brackets anymore because we know that we have associativity in that sense. And so this is equivalent of saying that H inverse G is in the stabilizer of X because it stabilizes X. X is a fixed point of that group element. And this is the same as saying that G Gx is H Gx, right? These cosets are the same. So what I'm saying here is that G and H collide if they give rise to the same coset of G sub X. Right? And so this means that the number of, if you look at G of X and you run over all G, so that's this thing, and you ask what's the size that I'm getting, then the collision will reduce the size, you won't get all of X like that. And so the size of that will be, because of these collisions, will be like 1 per coset. So the size of G of X will be the number of cosets of g of x in G. And note that here it's kind of on the set theoretic level. I am not saying that g of x is a normal subgroup of G, because it's not necessarily a normal subgroup, but it's still, in terms of subsets and congruency classes and so forth, that's a valid statement to say. And this implies that the orbit size of x, which is this thing, is, well, it's g over g of x, because that's the size of that, and g sub x is the x stabilizer. So what I'm saying here is that the orbit of x times the stabilizers of x in sizes is the size of the group itself. Good, and that will be useful for us, because we'll understand what stabilizes things, and that will enable us to compute the orbits of, in our context, of some actions. Okay, yeah, so that's all I needed from here. And as I said, you should make sure that you know all of these, like basic facts from Galois theory. I'll prove one of them that appears here, which you probably haven't seen, and then you can go on to talk about normal extensions. I will say that the majority of the proofs from these parts we actually are not going to prove. These will be, I will prove them in videos, but these are addendum videos to the actual course that you're welcome to see, but I'm not going to assume that you have seen them.